So, so thank you for coming today. This was a very short notice for let's say for a small conference, small workshop. So I'm sorry for the ones who were not able to come because of this short notice. But anyway, we're there, and we were able to have a full day of presentation about essentially meshing. And so I've not done that for a long time, so I'm going to present just a small presentation about GMSH. As everybody knows, we are with Christophe Guezen, the two main developers of GMSH, and I'm going to present our view of the past and the future, and explain what and maybe put in context the other talk from the team that are going to be presented today. So just a brief presentations for the ones who don't know both of us, Christophe Guezen and myself. So I'm professor at Université Catholique de Louvain in Belgium, where I lead a team of researchers, and we work mainly on mesh generation and higher method for PDEs. So I'm working less on higher method for PDEs since 4 years now. Maybe I'm going to go back to that subject at some point. Okay, our current main subject is hex meshing, but we do many other things. And so I've been cooperating with Christophe Guezen for now more than 20 years. It's been a long time. Yeah, and so Christophe has pretty much the same background as myself. For the story, we just met. He was starting his PhD when I was finishing it, so you can count what is our age difference. Okay, so and since that period, we have really worked together in a continuous fashion on many topics, but one of them is of course Gmsh. And so we both like to to write code. So I remember my my PhD advisor told me that when you will become professor at some point, you will stop to code. That was his motto. He says, yeah, when you become important, then you stop writing code, you make other people writing code. So we thought that was a bad idea. So we still write code, and I hope we will write code to the end, let's say, let's put it that way. Okay, what is Gmsh? I mean, I looked this morning to put the numbers to be very precise on the numbers I'm putting. So it's an open source code that does actually essentially meshing. It's a end user product, let's put it like that. It has a full graphical user interface that we less and less use and replace today by an API, which I will talk very briefly. So there is a full API where you can access in quite efficiently most of the algorithms and most of the data. You can exchange data, for example, with other code through Python, C++, or Julia. Oh, and today, today Gmsh is about 500k lines of code. I did the actual count this morning on the master branch. It's a little more than 500k lines of code, so it's slowly growing, like 500,000, 65,790 lines of code. And most of them, of those lines, were written either by Christophe or myself, okay? And there are more and more core developers now, thanks to our new continuous integration, continuous development platform. So we have about 100 users, developers that have produced more than one commit, that have actually done one commit. There are about 1,000 people on the mailing list, but we are abandoning the mailing. We are giving up on the mailing list. So we thought that this is a thing from the past, and so now we're moving directly to Git for users to complain, put some issues, and maybe solve these issues. There are lots of downloads per month, and of course we are between scientists, and we have to say about that we are all subjected to appreciations of our universities and rankings, etc. So we need sometimes to publish. So we did a publication in 2009, and this publication is now has more than 5,000 sites and is the most cited paper of the International Journal of Numericals in Engineering of all time. And so it is funny because this publication is essentially a publication without science. There's nothing new. It's just an explanation of the code and in quote, philosophy of the code, which is quite funny. It's not the first time when you look at paper from Jack Dongara that has wrote about LAPAC or BLAS. Nobody actually reads those papers because they are very low level and very uninteresting, but there's a lot of citation because everybody uses LAPAC and BLAS. So people like Jack Dongara are among the 10 most cited people in computer science, but nobody actually read those papers. Maybe I'm a little bit tough on that, but I think it's true. Anyway, our history is quite long. We did a first public release in 1998, but that was a shame. We should never have done that because that was the worst piece of code ever produced. And so we started really in 2006 with the first funding, in fact. Électricité de France gave us money to include Open Cascade as a CAD modeler in Gmsh. That was the first release. And we were very surprised at that time that there was tens of people in EDF and in the CEVA that were actually using Gmsh, while we were thinking that nobody would ever use that kind of sick code. And so we started to work on it a little more with this encouragement from people from EDF. And we went through all the items here. And the main change, essentially Gmsh 4 in 2018, when we moved slowly from an old-fashioned script, input script to an API, and this has made a lot of change in the user community. People were using the GUI, and now people more and more use the API, which is pretty neat and, in quote, unbreakable, in the sense that we only use doubles, strings, and list of those things, and integers, of course. And so, as you may know, at the same moment, a little earlier, I get a ERC Advanced grant. So we worked a lot on machine-related subjects. And so I'm not going to talk about the thing that people from my team are going to talk today in this presentation. I'll let them the floor for that. So in 2021, we moving to Gmsh 5, and I'll talk to you about, a little bit about our predictions on that. Okay, so it's funny that to talk about strategic choice of a software that has been built, I mean, without any strategy. So we didn't have any strategy at start. We didn't have any plan. We didn't even plan to make this software live for more than 2 years. So the strategic choice is a post-processing step. Is say, why were we able to live so long with this software without giving up? And so we just found out that because we were very bad programmers, we were only able to write very simple C++, not very elaborated, I would say, construct in C++ at the beginning, at least. So that was the right choice. Choosing very simple constructs allow that the code is easy to compile, can be supported for a long time on very strange platforms, on clusters, and etc. So that was a very good choice. And so I remember I've met the guy that has created Kitware, and we were office mates in US, and the guy told me that we should use FLTK as a GUI, let's say a toolkit for doing the GUI. So we were first thinking about very complicated things like, don't remember what we were thinking at the period, but FLTK is still alive and has been a good choice. It was not strategic, it was just, it was hazard that we did this good choice. And so Gmsh is very easy to distribute thanks to those choices. It's easy to install, it has zero dependency on installation, and when you run the software, the GUI, on the platform, it takes less than a second to pop up. This is something that people have found to be very interesting. You may know some software that take 1 minute just to pop up, to load lots of external libraries dynamically, etc. And this is something which, so Gmsh is one big executable with everything embedded, including the GUI. So it gets quite fast. And so we handle a lot of third-party libraries. Some of them must be installed by the user, and some of them are already integrated in Gmsh. So we have, for example, Banji, Metis, Concord. We have specific agreements with the developers to redistribute the code. So even when those codes cannot, in principle, be redistributed, this is the case of Metis, of Concord. This is the case of MUMPS. We are working on Gmsh 5 to have a fully integrated MUMPS support in Gmsh. So user shouldn't have to have MUMPS to download MUMPS from their site to get MUMPS. And so funding is important. You may think it's just in science, funding is not important. Everybody knows it's important. We started in 2000 to be funded, and just found out that doing open source and being a little bit renowned allows to get funding. I mean, this is something European Union is pushing forward a lot, is to promote open source. And when you say, okay, we have a very used open source software and we want to develop it and put new functionality, put new science in it, and so they are very happy, and it's a plus on your proposal. So we've developed a community infrastructure, GitLab, to be it's a GitLab, and we've made the choice to do a lot of documentation to allow people to use it. But we must confess that if you go on YouTube and type Gmsh, there are zillions of tutorials, and we've done none of them. That's the good point to have become a little bit renowned, is that people are doing the job of tutorials and etc. There's a lot of universities where Gmsh is used as the basis for doing meshes for the finite element course. So people in those universities make YouTube videos to explain how to do this and that. And so all of that creates a community which is quite interesting to have, to not to work too much on those tutorials. So people do those things for ourselves. And so all the scientific aspects are in journal papers. In terms of licensing, we do double licensing. So we have the copyright of Gmsh, of the core of Gmsh, Christophe and myself. There are contributions, external contribution, which have their own license that must be compatible with the GNU version 2 or later. And we double license the core to companies. So that's I would say the economic model that we've put in place. A core, which is GPL version 2, that is belonging to Christophe and myself in terms of licensing, and we double licensed with the if needed. So we for the other professors and researchers, we had to have an agreement with our universities to allow us to keep those copyrights and those property of the code. And our argument was very clear. It was, we get funding, you are happy that we get funding, we need to have this thing to allow us to be flexible, for example, to change license, to do strategic choices, and not have to ask, I would say, the copyright owner different than ourselves. And it's more interesting, it's more fun to own your own code. So I just advise you to do the same with your universities if you can. Okay, so we have essentially 4 modules in Gmsh, and I'm not going to talk a lot about that. There's geometry mesh, so I'm not going to talk about solver and post-processing. And you can access those modules at 3 levels through the GUI. And so the newbies and new users use a lot of GUI. Then when you know it a little bit, you know that we have a dedicated language, which is GeoLanguage. The funny thing is that I wrote the parser for the old guys in Lex and Yak in 2001, and it was really ugly. But still, the geofiles of 2001 can still be read today. So we have a backward compatibility which is more than 20 years. And so this is something which we were not expecting to do, but we found that it's a security for the users. We are absolutely backward compatible for a long time, and it takes a lot of time because I would say just the numbering of the model entities inside Gmsh has to be consistent throughout the years, and this is an issue. I can tell you this is a big issue. And then in the last version, in the last years, we prefer to interact with our algorithms through Python or C++, at least through an API. And so this is the third version of the API, I must tell. We started 10 years ago using Swig and doing wrappers, wrapping everything in Python, in MATLAB, in Julia, and that was a mistake because we were presenting, to the users, to the developers, all our classes and objects and structure. It's a mistake because, of course, you can break everything if you do that. So we went backwards and discussing with other teams that do that. We just now have about 100 functions that actually allow you to efficiently access algorithm and data structures from Gmsh, not more. So you cannot access our internals. We did all these APIs is only through simple data types like doubles, integers, and strings, and list of those things, period. Okay? And so, our, I would say, meshing in code philosophy is a surface to volume philosophy, in the sense that we have a representation of the geometries, which is a boundary representation, which means that we know the model through its boundaries. Okay, so a curve has two ends plus a geometry, a surface has a curve that bounds it plus a geometry, and a volume has a set of surfaces that bounds in, and its geometry is of course R cube. It's simple geometry. And so with that, all our algorithm work on that, I would say, philosophy, which means that even though we could have, like here, discrete surfaces as input, triangulation, we go back to that representation. So we create parameterizations of the object, of the discrete objects, to allow our surface measure to work in a parametric plane and to do the job in the same fashion, either whether you're discrete or you're, let's say, continuous, you use a CAD. So this is essentially a CAD. Here, the representation is the ocean. So it's the data come from essentially, I think, NCAR or NASA or whatever. And this is, the input is in triangulation. Okay, so that's exactly what we're saying. We have 4 levels of entities in Gmsh regarding to their, with respect to their dimension, and we have a representation which is called bidirectional. Every curve knows its ending point, and every curve knows, for example, all the faces that that are adjacent to it. So we know that. So we know this is not a good representation for a BREP. There is a lot of things missing, like loops, and this is enough for meshing. That's it. That's exactly what I would say. What is important to know is that we don't have an internal geometrical representation. If there is a NURBS, okay, the NURBS, its representation, the way it's interpolated, the functions, the order, all those things are done by cat kernels that we directly interact with. So we have a certain amount of cat kernel that we can interact with, which means that we have to do we do specialization of classes of model entities for Parasolid, for Open Cascade, and we have our own very small representation that doesn't have NURBS, for example, that have only planes and B-splines and things like that. So the idea is that when you load a CAD model, we don't do any translation. We just directly go to the API of the CAD model and ask for it. So since Gmsh 4, we have a Parasolid version of this interface that we cannot, of course, distribute for free or even put the code that actually interact with the API, because Parasolid doesn't want anybody to see their API. So it's a private API. Okay.
Just, can you finish in a few minutes?
Yes.
2 minutes? Or
yes, 2 minutes. Okay, so that's exactly what I've said here. I just wanted to say that in the mesh module, we have worked recently on a certain amount of parts. So I just want to point out 3 things, and I will let my colleagues to talk about everything that is about the extreme DRC project. What you have to understand is that in a CAD model, as you know, Riemann told us long ago that if you have a sphere cannot be parameterized using one. The atlas needs at least 2 maps, but in a CAD model, there is only 1 map for a sphere, and you have singular parameterization. You have to be able to deal with that, and so we recently have found a way to deal in a robust fashion with that. So you see here, for example, this is the surface mesh in the parameter plane of an ellipsoid with a hole here that is able to produce in the parameter place a mesh that is valid in 3D. We also, with Pierre-Alexandre that is in the room, worked a lot of being able to make these discrete models, models made only by triangulation, fit to our, let's say, a plan, which means that we need to do a full CAD model with this parameterization. So Pierre-Alexandre worked a lot on his PhD on that, and so now we have a really robust pipeline that you take a triangulation. For example, here there's a triangulation, we can remesh it in an automatic fashion. This is another triangulation, and we can remesh it with only 1 press button. Okay, and so we also with Celestin worked on fast 3D meshing. Our 3D mesher in Gmsh 3 was so slow that users were not really liking it. Now we think we have the fastest 3D mesh generator of today's fastest mesh generator, and you see those kind of performance that we have. We can generate on a simple computer meshes of hundreds of millions of tetrahedra in about 3 minutes on a simple laptop, which is extremely fast, which is in an industrial context very, very convenient, because this makes the people quite happy. So I'm moving to the conclusions. Okay, I'm not going to talk about that. So I didn't talk about that, but we now have a good constructive geometry, solid geometry module in Gmsh that allows you to generate quite complex CAD models, or at least to modify them in an easy fashion, and the API is great. And so we have many exciting development in the pipeline. We are still working a lot on high order meshing, and we have a European project where we work a lot on that. We do hex meshes, hex dominant meshing, that will be presented today, and Maxence will present semiotic block structure decompositions, boundary layers. So thank you for your attention. If you have questions, I'm there.
Okay, so thank you, JF. Now, don't hesitate if you have questions on this talk and Gmsh.
I have a coffee.
So you can ask the question on the public chat or directly by speaking.
No questions.
It was very detailed. Okay, so
maybe I have a question. Hello, Jean-François. What is the big next step for Gmsh then? So you have shown us what has been achieved lately, but what would be next from your point of view?
CFD. this is the next step. We hope in 2021. So Gmsh is used a lot in computation, in solid mechanics, in electromagnetism, and in, I would say, niche subject like microsystems, electronics, and things like that. We practically have no users in CFD because our boundary layer machine capabilities are, let's say, basic. So in collaboration with other teams and within the team, we really want to go forward and have, in 2001, CFD capabilities. And I would say this is, there are two parts. One is, as usual, if you want to do that, we are going to do a simple, let's say, a standard implementation, so no science. It will take me time, and Christophe too, and maybe find and Maxence has some ideas on that alternative method to do something which can be new and interesting. But boundary layers is something in 2021 that must be there in terms of our, let's say, community, because we just found out that nobody in CFD used Gmsh.
Okay, thanks.
Are there other questions? Don't hesitate. Okay, so if no question, we'll go to the next talk.